Hello and welcome to this third video in a series on nuclear chemistry aimed at National 4-5 level. And today we're talking about radioactive decay, which is what's actually happening when radiation is produced. Because we know that some materials are radioactive. They produce radiation. Some of them emit alpha particles or alpha radiation. And these turn out to be helium nuclei made up of 2 protons and 2 neutrons. Others emit beta radiation, or beta particles. Now, beta particles are electrons, but they are not the electrons you normally find orbiting the nucleus. We'll be coming to that in a minute. And finally, gamma rays, which are a form of high-energy electromagnetic radiation. Okay, so we're going to look now at why some of these materials are radioactive at all. Okay, let's consider this graph here. What you've got for the known isotopes of the elements, you've got the atomic number and you've got the number of neutrons. So on the bottom you've got number of protons, up the side you've got number of neutrons. Okay, now those dots represent the stable isotopes. These are the ones which we know are stable, that don't really give off radiation. So this line here is the line where the number of protons is equal to the number of neutrons. Okay, let's look at a couple of examples here. Down here, low atomic number, low number of protons, say about atomic number 20. Your number of your stable isotopes around about the same, 20 neutrons. So down for these low atomic numbers, where you've got a smallish number of protons, you only need the same number of neutrons for the isotope to be stable. But let's look at what happens as we increase the number of protons. Let's go up to 60 here. And as we can see, we need more than 60 neutrons. We need about 108 there. So as the number of protons in an atom increases, it also increases the number of neutrons you need to get a stable isotope. That's because the neutrons help hold the nucleus together. Without the neutrons, the repulsive force between the protons would just tear the nucleus apart. So unstable nuclei decay in ways that turn them into more stable ones. So let's see what forms of decay we've got. Let's consider alpha decay. This involves the release of alpha particles. Now, an alpha particle is a helium nucleus, 2 protons and 2 neutrons. There we go. That's kicked out of the nucleus. Now, the effect of that is it decreases the number of protons by 2. So you've also therefore decreased the atomic number by 2. That means you've produced a different element. Remember, it's the atomic number that defines the element. If you change the number of protons, change the atomic number, you change the element. You've also decreased the mass number by 4. That's 2 protons and 2 neutrons. So you've produced an atom of an element with atomic number 2 lower than the original one. Okay, let's look at beta decay. Beta decay, remember, is made of electrons, but they're not those that we're seeing in the diagram at the moment. Let's take one of the neutrons in the nucleus. Now, just every so often, a neutron can break up to form a proton and an electron. And it's that electron that kicks out of the nucleus as beta radiation and as beta particles. So, your neutron turns into a proton and releases an electron. Bing, like that. Off it goes. Notice that has no effect on the mass number. You've exchanged a neutron for a proton, so the mass number doesn't change. But it does turn the atom into one with an atomic number bigger by 1 than the original, because you've got one more proton now than you had before. Gamma decay, that's electromagnetic radiation, so no particles involved here. Just a burst of electromagnetic radiation. So that's going to have no effect on the atomic number, and it's going to have no effect on the mass number. So how do we represent these various things that we've been talking about, these various particles? So take the proton. We can represent the proton like this. Mass number 1. Number of protons plus neutrons is 1. Number of protons, atomic number, is 1. And you've got a positive charge because protons are positive. Neutron, represented by an N. Notice atomic number 0. No protons here. But your mass number is still 1. Protons and neutrons both weigh 1 atomic mass unit. You've got the alpha particle. We're going to represent that like that. Notice atomic number 2 because it has 2 protons. Mass number 4, 2 protons plus 2 neutrons. We can also represent it like this. The beta particle, the electron, we're going to represent like this. Notice mass number 0, no protons, no neutrons, so mass number 0. Now, the atomic number here is going to be -1. Now that might seem a bit weird, but it allows us to do a nice little accounting trick later on. And again, we can represent the beta particle with the symbol beta. Gamma rays, dead easy, just gamma, and all zeros, no charge, no mass, and no atomic number. Okay, so we can use these symbols to write decay equations. Key rules to remember when writing these: the total mass number must be the same on both sides of the equation because you can't make mass disappear. And the total atomic number will be the same on either side as well. Now that may sound surprising, but let's look at how that works. Let's consider the decay of actinium. Now actinium, when it decays, becomes thorium. So actinium-228 becomes thorium-228. But let's see what else must be produced. Notice the mass number hasn't changed. So whatever else is produced has a mass number of 0. So that's either beta or gamma, because alpha radiation has a mass number of 4. Okay, let's look at the atomic number. The atomic number's gone up by 1. Now the particle that does that is the beta particle. So this then is our other product. Notice, by the way, 90 plus -1 is 89. So the atomic number is the same on both sides. Okay, let's consider what happens to the thorium. The thorium also decays, and it produces an alpha particle. Okay, we can work out what else is produced now. Let's go back to the mass number. We've got 228 over here, but we've already got 4 on the other side. So the mass number of what's formed must be 224. Your atomic number is 90 here, but we've already got 2 on this side. So the atomic number of what's produced must be 88. And there it is. Radium-224. Okay, just check that the atomic numbers on the left and right both add up to each other, and the same with the mass numbers. Remember, gamma decay changes nothing. Okay, to sum up, radioactive decay makes nuclei more stable. That's why it happens. Alpha decay involves the release of a helium nucleus. The effect of that is to reduce the mass number by 4 and the atomic number by 2. Beta decay, caused by the decay of a neutron. The neutron breaks up to form a proton and an electron. Now this has no effect on the mass number because you're just swapping a neutron for a proton, but it does increase the atomic number by 1 because you've gained 1 proton. Gamma decay has no effect. You'll need to know the symbols, and you should be able to write decay equations. Now, writing decay equations, like anything else, best achieved by lots of practice. Okay, thanks for listening. Bye for now.